Hi, okay. So now we're going to calculate measures of location. First thing to do would be define what is a measure of location. And we're going to write it here on our whiteboard. Okay, so measure of location. Your measure of location tells us where, oops, that's probably not the greatest. It tells us where the majority, where the center Okay. Tells us where the center of the probability distribution is located. So it tells us where the actual center of our data occurs. Okay. So in other words, just think of average male height, right? There are all different values for how tall men are. Men can be 4'8". Men could be 7'6". Men could be 6'6". Men could be 5'6". Okay, there's all different values that male height could take on, and there's obviously probability associated with it, right? It's very unlikely to run into somebody who is 7 feet 2 inches tall. It is very unlikely to run into a man who is 4 feet 9 inches tall. It is very likely to run into somebody who is 5 feet 10 inches tall. Okay. So a measure of location is telling us where exactly is the center of the probability distribution located. Okay. In other words, what is the actual middle of male height, right? What is that value? Okay. It tells us where the center of the probability distribution is located. Now, there's three common measures of location in statistics. Okay. When we're doing quantitative analysis, the three most common measures of location are the arithmetic mean, aka the average, but it is not an average, it's the arithmetic mean. Okay. And there can be a population mean and a sample mean, which is what we're going to work with in this class. Okay. An arithmetic mean, of which there's two types, right? Population mean and sample mean. There is the median, and then there is the mode. Okay. So in this class, the three most common measures of location are the arithmetic mean, the median, and the mode. We can just call it the mean, the median, the mode. Okay. I understand if you call it average. I get it. It's the average, right? It is technically the arithmetic mean. Okay. That's what we're going to work with in this class. Okay. So let's calculate some of these, right? First, let's do the arithmetic mean. Okay. Let's just pretend, right? Let's pretend that we have IBM stock prices. Okay. Let's make up a data set. Let's pretend that our IBM stock price is, let's take 5 days, Monday, Tuesday, Wednesday, Thursday, Friday. Let's say that it was 95, 98, 104, 92, and 10 whatever 7. Okay. So on Monday, IBM stock was $95. Then it was $98 on Tuesday. Wednesday, it was 104. Thursday, it was 92. On Friday, it was 107. Okay. If all we care about is the price of IBM stock last week, okay, if all we care about is last week, if that's the thing we're interested in, if I want to know the true actual price of IBM stock last week, if that's what we care about, just last week, because obviously IBM, International Business Machines, that company's been around for at least 120 years, I believe, right? It started in the early 1900s, if not earlier. But could be a little off on the timing there, but it's been around for, decades. If all we're interested in is the average stock price, the average, if all we're interested in is IBM's stock price from last week, then that means that that would be a population. Okay. If all we care about is last week, the stock price last week, right? Last Monday, Tuesday, Wednesday, Thursday, Friday. That's all we care about. Then that is the entire set. The entire set of IBM's stock price would have occurred last week, last Monday, Tuesday, Wednesday, Thursday, Friday, which means that we're looking at the entire set of everything we've ever cared to look at, right? That's the entire set of values or objects of interest. And therefore, we would be looking at parameters. If we have the population, that means we want to find the parameter. Okay. So if we could calculate the arithmetic mean of last week's IBM stock price, if we calculate that arithmetic mean, then we would have the true actual value of IBM stock price last week. Okay. So let's calculate this arithmetic mean. In order to calculate the arithmetic mean, we have, right? Remember, there's two types of arithmetic means. There's a population mean and there's a sample mean. Okay. Here we're going to work with the population mean first. The population mean is something that is known as mu. Okay. I should try to draw this as well as I can just for, oops, okay, population mean. And mu, which you can Google mu. You just type in population mean mu and it'll come up. But I want you to be able to see it looks like a funny M. Okay. It's mu, mu. That is a Greek letter. In quantitative analysis, anytime you see a Greek letter, you are working with a parameter. Anything that's in Greek is a parameter. Okay. So we have mu equals the summation, which is a funny looking E. This is actually capital sigma. Okay, capital sigma. If you want to Google it to see, what exactly should it look like, because I can't do it great on my graphing tablet. But if you Google, capital sigma statistics, SIGMA, sigma, this stands for the summation, summate all of the terms. So we are going to summate all of our X terms and then divide by capital N. Okay. Capital N is the number of observations in the population. Okay. So what's an observation? It's just simply one element or one unit or one part of our data set. So take this 95. That would be observation one. Observation one started on Monday. That's observation one. Tuesday, that's observation two. Wednesday, observation three. Thursday, observation four. Friday, observation five, right? So an observation is just a single unit, a single element of your data set. We call those observations. So what this formula is saying is that our population mean, the population mean mu, right, which is a Greek letter. If it's a Greek letter, it's a parameter. We also know that it's a parameter because it stands for a population mean. It's a parameter because parameters are characteristics of populations. Well, this would be a characteristic of a population. Okay. That parameter or parametric value, how do we calculate that? Well, what we do is we summate all of the x terms. Okay. So in other words, we add up the x's, but we summate the x terms and then divide by the number of observations in the population. How many observations do we have? We have five. We have five observations. Observation one, observation two, observation three, observation four, observation five. Okay. So what is this formula saying? Summate all of the x terms and then divide by the number of observations in the population. What does that mean? It just means do x1 plus x2 plus x3 plus x4 plus x5 divided by the number of observations in the population. How many observations? 1, 2, 3, 4, 5 divided by 5. Okay. So what this is telling us is, again, summate the x terms. How many x terms do we have? We have x1, which is 95, x2, 98, x3, 104, x4, 92, x5, 107. So we have to add up all of those x's and then divide by the number of numbers, right? The number of observations, which is 5. 1, 2, 3, 4, 5. So how do we do this? We do 95 plus 98 plus 104 plus 92 plus 107 divided by 5, which is equal to, I have to do this on a calculator very briefly, if you could bear with me. So 95 plus 98 plus 104. And you should be doing this at home as well, right? Plus 92 plus 107. That equals 496. That's what I got. I could have made a mistake. I'm not sure if I did. I don't think I did, but obviously I could have. I'm human. 496 divided by 5 gives us 99.2. Okay. So, but what I'm going to do is I'm going to double check and make sure I did that correctly, because you should get in the habit of double checking your work. It's always just a good habit to do, whether it's writing, just proofread, right? If it's mathematics, right? Just check it again. Try to make sure you get the same answer. 95 plus 90. Oops, that's it. I almost did it. Plus 98 plus 104 plus 92 plus 107 equals 496. I got the same answer divided by 5, 99.2. Okay. So that means, what that's telling us is that our average, the population mean, and I said average, I'll tend to do the same thing, right? Okay. I know that, in everyday parlance, we use, average mean, stuff like that. It is technically the arithmetic mean, it's population, but everybody, we say it in the average. When you're programming it into Microsoft Excel, you don't type in arithmetic mean, you type in average. Okay. So our population mean, right? What is that? Well, the population mean is a parameter, and it is the true actual value. It's the true actual average of our IBM stock prices from last week. Okay. Well, what is the true actual average of our stock prices of IBM from last week? It's 95 plus 98 plus 104 plus 92 plus 107 divided by 5, which is $99.20. So if somebody asked you, what is the true, actual, real average stock price of IBM from last week? You would say, oh, it's $99.20. Okay. So that's the answer. But that's for the arithmetic mean. Okay. The population arithmetic mean. If we wanted to do a sample mean, then we have to calculate something different. Okay. Sample mean. A different formula, and I'm going to pick a sample now. I'm just randomly going to pick it. And the sample, again, is just a portion of the population. Okay, so I'm just randomly picking my sample mean. My sample mean, I'm no longer using mu. Okay, this, okay, that is only for the population mean. Okay, mu, the funny m, right, the Greek letter mu, that's only for a population mean. This has nothing to do with a sample mean. Okay, two types of means, right? The arithmetic mean, there's a population mean, there's a sample mean. If you want to do a population, you're working with mu, a Greek letter. So you use this. But that is not what we're doing when it comes to our sample mean. Our sample mean, we just use X bar. Okay. Yes, it's pronounced like that. It's pronounced X bar. Okay. X bar, B-A-R, with a bar over it. X bar. Okay. That is the sample mean, X bar. Okay. So we use mu. We use mu for the population mean. For the sample mean, we use X bar. X bar is equal to the summation of X divided by lowercase n. It's not capital N, it's lowercase n. Okay. Lowercase n is the number of observations in a sample. In a sample. Okay. And yes, this does make a difference. If you ever go on to take more advanced quantitative analysis courses, like, say, elements of econometrics, it absolutely matters whether you're using capital N or lowercase n, okay? Because this is notation. You have to know whether you're talking about populations or samples. Remember, the whole point is we're trying to use these samples and their statistics to determine whether it's reasonable to believe something about a population and its parameters. Well, if that's the whole point of what we're doing, we absolutely need to know if we're working with the number of observations in a sample or the number of observations in the population. So even though it's just, capital N, lowercase n, big difference. Big difference. Okay. So what this is saying is summate all of the X terms and then divide by the number of observations in the sample. Okay. Let's just, why not? Let's just make this our sample. Okay. What is a sample? Sample is nothing more than a portion of the population. So if the population was last week, right, it was Monday, Tuesday, Wednesday, Thursday, Friday, I'm just taking Monday, Tuesday, and Wednesday and calling that my sample. It's a portion of the population. Okay. So summate the X terms and then divide by the number of observations in the sample. This would be X1 plus X2 plus X3 divided by 3. I have one observation, two observation, three observation, three observations in my sample. And then what I'm going to do is add up the value of Monday, the value of Tuesday, and the value of Wednesday. Then divide by 3. Okay. So again, how'd I get here? Sample mean is X bar. I'm going to summate the values of the observations from Monday, Tuesday, and Wednesday, and then divide by 3 because that's how many observations are in my sample. So I have Monday, Tuesday, Wednesday. I have 95, 98, 104. So 95 plus 98 plus 104 divided by 3. And this gives us 95 plus 98, 95 plus 98 plus 104, which I calculated as 297 divided by 3. I'm going to check my work again. As I said, 95 plus 98 plus 104 equals 297 divided by 3 is 99. Okay. So my X bar, my sample mean is 99. Okay. My population mean, if you remember back a couple minutes ago, my population mean was 99.2. Okay, so $99.20 versus $99. Okay, so here is the whole point of what we're doing with measures of location in quantitative analysis. Obviously, we're only working with 5 days for the population, so this is kind of simple, right? Our sample is only 3 days, but let's tack a couple zeros onto the end of that. Let's say that our sample was 300 days, and we're trying to estimate a population of 500,000 days, okay? The whole point of quantitative analysis, what we're doing is we are trying to decide whether this number, this sample mean, we are trying to figure out if this is a reasonable estimate or a reasonable approximation of this number, our population mean. Okay. If we're working with 300 observations in our sample and 500,000 in our population, this is going to be a big estimate, right? We're really working with a lot of data here. Well, what we want to know is this a reasonable estimate of that? For right now, it looks like it. Yeah, I mean, $99 versus $99.20. All right, that looks fairly reasonable, right? But when you're working with 500,000 observations, you might not know, how close you are necessarily. And that is the whole point of quantitative analysis. Quantitative analysis, in the next couple lessons, I'm going to give you the tools that you need, whether it's confidence intervals, hypothesis testing, linear regression, right? We're going to have the tools that we need in order to say, you know what? Yeah, I think the sample mean is a reasonable estimate of the population mean. Or you'll be able to say, you know what? I don't think the sample mean is a reasonable estimate of the population mean. I don't think so. Right? That's the whole point, is to figure out, based on this limited information, if what you generally believe to be, the whole point is to figure out if that's reasonable. Okay, that's everything we're doing here. Okay, so that's the population mean, and this is the sample mean. Okay, population mean was 99.20, sample mean is 99. Okay, now let's do the median, right? Remember, we have 3 measures of location. The mean, which we just did the population mean and the sample mean. Okay, so we have the mean, then we have the median, and we have the mode. Okay, so let's do the median now. I find that students tend to know what the median is from prior familiarity, prior classes you've taken, which, let's be honest, you probably should know what the median is already, but just for a quick review, or in case you don't know, right? The median is nothing more. Oh, I should erase that too. The median is nothing more than the middle number when you arrange from smallest value to highest value. So, median. Again, if you arrange all of your observations from lowest value to highest value, okay, so you just line them up in ascending order, right? Lowest value to highest value, then the median is the middle number. So let's take our data set here, 92, 95, 98, 104, 107. Let's put it in ascending order. We have 92, 95, 98, 104, 107. Once you line them up in ascending order, the median is simply the middle number. Okay, so this is the median because we go 1, 1, 1, 1. This is the middle number. It's the middle, it's the number in the middle. So 98. 98 would be the median. Okay. Now let's just pretend, let's pretend we also had 110. Okay, so in other words, we have 6 days now, right? 95, 98, 104, 92, 107, 110. If we had 6 days, then we would do 92, 95, 98, 104, 107, 110, right? Okay, so let's do the middle number. Okay, so 1, 1, 1, 1. Wait a minute. There's two middle numbers. How do we get the middle number from these two? It's very easy, right? You just do 98 plus 104 divided by 2, and that would give us 101. Okay. 101 would be your median from this data set. Okay. I just added in 110. Okay. My goal here was to show you when you have an odd number of observations, right? When you have an odd number of observations, here we have 1, 2, 3, 4, 5. That's 5 observations. So that 5 is an odd number. When you have an odd number of observations, the median will always be in your data set. Okay, it will always be in your data set. But when you have an even number of observations, 1, 2, 3, 4, 5, 6, 6 is an even number. When you have an even number, your median may or may not be in your data set. Okay, when you have an even number, you have to take the mean. You have to take the mean of the two middle numbers. So you have to do 98, 104. Once you calculate that mean, then you have your median. Okay. Uh, just as an aside, why do you use the median instead of the mean? Okay, one advantage of the median rather than the mean is it gets rid of really big numbers and really small numbers, what we consider to be outliers. Okay, so in other words, if you wanted to know, the average income of Jersey City, say, right? If you want to know the average income of Jersey City, you'd add up these, or let's say St. Peter. Let's say you want to know the average income of a student at St. Peter's, right? So you would add up all of the incomes of every student at St. Peter's and then divide by the number of students at St. Peter's. Okay, I mean, that's fair. But if you were to if St. Peter's was suddenly to have, 6 students who were all billionaires, that would raise the average income at the institution to make it seem like everybody is a millionaire, right? The average income of a student would suddenly skyrocket to $4 million, right? The average, because those six students, with the fact that they're billionaires, that would pull everybody else up with them. The same way that if if a professional basketball team walks into a room, suddenly the average height of that room would go up to 6'7", right? Suddenly the average height of that room, everybody's it seems like everybody's tall, but not really. Everybody's not tall. It's just that there's a few really tall people in the room, which pulls everybody up with it, pulls the average with it. Okay. Well, the point of the median is it doesn't matter whether, this number is 107 or 107,000. Okay. Obviously, if this number was 107, this would pull the average up, right? If it was 92, 95, 98, 104, and 107,000, the average of this is going to suddenly go way, way, way up. It's going to be like 90,000, or well, not 90,000, but in that ballpark. It's going to be very, very high. Be about 20,000. But if we take the median, all we do is cross this out, cross this out, cross this out, cross this out, and we find out that the middle of the data, right? Remember, this is measures of location. It tells us that the center of the data is located at about 98. Right? That's where the data is located. So it got rid of the influence that 107,000 would have put on everything. The same way that, if there were 6 billionaire students who sign up at the institution, well, when you're ranking them for income, you would eliminate the six people with the lowest incomes and six people with the highest incomes, the billionaires. And then we would start getting closer to the true actual center of where the data is located, right? That's the point of the median, is it gets rid of really small observations and really large observations, what are known as outliers. Okay. So that's the point of the median. Median's pretty simple, right? It's the middle number. You just rank your data in ascending order, lowest value to highest value. If you have an odd number of observations, it's the middle number. If you have an even number of observations, you simply have to take the average of the middle two. Okay. You just take the mean of, your two middle observations, and that gives you your median. So that's the median. Fairly simple. The last one to do is the mode. Students generally know what the mode is as well. Let's click this. We got to erase that. And the mode is nothing more than the value of the most common observation. Okay, the mode is the value of the most common observation. So here we have 92, 95, 98, 104, 107. There's no mode there, right? Let's just put them 92, 95, 98, 104, and 107. Okay. Each value occurs only one time. Each value occurs only one time, so there is no mode. This data set does not have a most frequent observation. However, if we had another 98, okay, well then 92 happens once, 95 happens once, 104 happens once, 107 happens once, 98 and 98, well, that happens twice. So then the mode of the data set would be 98. If we had 98 happen twice and 92 happen twice, right? So 92, 92, 98, 98, 95, 104, and 107, those only happen once, but 92 and 95, 92 and 98 both happen twice. Then we would have what's known as bimodal data. Okay. So in other words, you can have two modes, okay? But the mode is simply the observation that happens most frequently, okay? Um, so, in summary, those are our three measures of location: the mean, the median, and the mode. The one we are going to work with by far the most frequently in this class is the arithmetic mean. Okay, so we have arithmetic mean, there's a population mean, there's a sample mean. We're going to work with those in this course, and we have the median and we have the mode. Okay, the three of those, the mean, the median, and the mode, those are our measures of location. The point of them is to tell us where the center of the data within a probability distribution is located. Where is the actual center? Out of all the speeds that you end up driving on the New Jersey Turnpike, what is the actual center? What's the average speed you do, right? Out of all the prices of IBM stock that happens throughout the course of a trading day, right? All the prices that happen, what is the actual average, the mean price, right? What's the center price? Where does all that difference, all that differential data, differential values, where is the center of it located? Okay, so those are our measures of location. In the next video, we're going to talk about measures of dispersion, which is how spread out our data is, right? Okay, so that'll be coming up next.